Good afternoon again. So this is our second session of the sixth lecture. And now we're going to look at a very simple model of innovation or innovative process. Okay. So here, time is continuous. So let me maybe I should do this. Okay. So time is continuous and starting at some initial period. Okay. Now, the production function for the entire society is very simple. So we forget about human capital, we forget about physical capital, okay? So we just assume away these things. We are just looking at a production technology that is linear in labor, okay? And there is this productivity term, okay? So AT is the overall productivity variable of this economy, okay? Now, LYT denotes the labor, the amount of labor employed for the production of good, okay, good Y, at time T. And AT is the productivity of each worker, okay? Now, this productivity can be increased. How? Well, this is this R&D technology, right? So there is this R&D technology. So if you employ some workers, okay, in that R&D sector, this is LAT, those workers employed in the R&D sector are going to use the existing state of technology, existing state of knowledge AT, to produce new knowledge, right? So remember, by definition, this thing denotes the time derivative, right? So A dot T is the amount of new technology that is produced. And of course, we are here assuming that new technology directly makes economy more productive, right? So if you have new technology, after that instant, you become more productive, right? And I mean, you can understand this part as a production function itself, right? So there's labor and there's productivity, and then there is this term theta because we need a measurement. We need a way to discriminate, to differentiate the measurement error of output from the measurement measurement unit of. So we want to differentiate the measurement unit of output from the measurement unit of knowledge, because otherwise it would be apples and oranges, right? But then the resource constraint for this economy is given like this, okay? So this is the resource constraint. How? Well, the total supply of labor is L. You may imagine that this is population or working age population or labor force. And the society has to decide how many of these workers are going to be used in the production of the goods, and how many of them are going to be used in R&D. Okay, so that's a decision to be made. Also, we have population growth or labor force growth. Okay, so this part looks like the Solov model. Okay. Now, obviously, if in the full version of this model, there are firms. These firms are using these technologies, and they optimally choose how much of the labor to be employed in R&D, right? Now, here we are taking a shortcut and directly say, okay, total workforce, a gamma star fraction of it is going to be employed in R&D. Okay. So the remaining, so you have this total labor, okay. Gamma star LT is going to be employed in R&D. 1 minus gamma star LT will be employed in output. Okay. So here, obviously, I'm taking the shortcut because in the final, in the fully fledged model, there will be an optimization problem on the side of firms. So firms will take everything given, and then they choose how much labor to be employed in the R&D sector. I'm taking the shortcut here. So gamma star, suppose that gamma star is determined already. Okay. Now, if this is the case, see what happens. So let me use this area to show you the growth. Okay. Now, the growth rate of technology is defined in this way, right? Theta LAT. So what is LAT equal to? Well, it is equal to gamma star LT. Okay. So what is output per worker? Well, output per worker will be YT divided by LT, right? So what is YT? YT is AT LYT divided by LT. So YT will be equal to AT times 1 minus gamma. Okay. So you see, as long as we know gamma, because gamma is the only decision to be made here, so decision to be made here in this economy, right? It is the only allocation problem. So we understand that if that's the case, the growth rate of the economy is this. This is now G, right? And that growth rate is the relevant rate to explain the growth rate of GDP per capita or GDP per worker. Okay. So what do I see here? I see that the total amount of workforce employed in R&D actually determines how fast we grow, right? How fast we grow. So that's the simplest model of innovation that you can imagine. Okay, because there is only one decision to be made, and actually we are taking a shortcut to not to look at the firm behavior at the micro level, and we just basically said, okay, there would be some optimal level of gamma, okay, and that optimal, whatever it is, it's there, and then starting at any point in time, right, any point in time with a given level of technology and a given level of population, this economy grows with a particular rate, and since the population itself is growing according to this definition, the growth rate itself accelerates. Okay, so that problem I'm gonna discuss it in a moment, or perhaps next week. It is called the scale effect problem. But for now, what is important is to understand this: the growth rate changes positively with gamma. So if you have more engineers and more inventors and more scientists, if you allocate a larger amount of resources to innovation, obviously you grow faster. Okay, for this reason we have the technology firms, and for this reason we have governments that try to increase the long-run growth rate of the economy through technology and industry policies and all this stuff. Okay, so to summarize what we learned here, the growth rate will be a function of and this is the growth rate of, so GDP per worker will be given in this way: 1 minus gamma star. Okay, and this itself is LAT. Okay, so from this, of course, you know that the growth rate of y will be equal to growth rate of A. Okay. Now, let's think of this entire thing in terms of time. Okay, suppose that time is on the horizontal axis and yt is on the vertical axis. So obviously, the growth path will look like this. Okay.
Hocam y diğer y değil mi? Böyle daha dik yazdığımız.
Anlamadım.
Ya iki tane y.
I don't.
There are two y's.
Okay.
One is yt eşittir yt over lt ya.
Hı hı.
Bu sayfada yazdığımızda diğer yt olması gerekmez mi?
No. Let me show you. This is what you have, right? The aggregate GDP is equal to AT times LYT, right? Now I'm dividing this with LT to get GDP per worker. Okay. Now the ratio of LYT to LT is 1 minus gamma, right? You get it now?
Thanks.
Okay. So the growth path of GDP per worker will be like this, and of course it will be the growth rate of, so the same growth rate will apply. How do I know that? Because of this, right? So the growth rate of it will be like this. So if this is AT. Now you may imagine a change in gamma, okay? So how do you understand a change in gamma? Okay, suppose that gamma star is increasing. Suppose that the government now, through the planning mechanism, through the development plan or something like this, the government allocates a larger fraction of workforce, okay, a larger fraction, gamma 1 of workforce to R&D. So suppose that change will happen at that T, okay? Let's say T hat. So how does this whole thing change? Any ideas? Well, the idea is this. Obviously, since gamma is larger, the growth rate will be faster, right? So the growth rate will be like this, right? And what about GDP? Well, GDP growth rate is faster as well, but GDP will decrease initially, right? Because of this. So initially it will be lower, but then will grow at a faster pace, right? Does everybody get it? So let me draw the logarithmic versions. It is easier to see with natural logarithms. Why? Because logarithms will make them smoother, right? So you have that type of stuff. Until there, and you have that until there. This is, let's say, ln y. This is ln a. Okay. Now, in the case of A, without the policy change, it looks like this, okay? And without the policy change, it looks like this. They're the same, basically, the same slope, right? Now, when the policy changes at that T hat, GDP goes like this, okay? And output first decreases because of this again, right? Then it also goes like this. Okay, so what happens here? The society makes a sacrifice today, right? The society makes a sacrifice today to have more output tomorrow, right? So in that sense, technology is like capital, right? If you look at this equation, technology is like capital, right? There's no depreciation. We assume that delta is 0, right? And there's new investment into technology, and technology accumulates, knowledge accumulates. That's exactly the idea, right? In capital accumulation, you try to increase tomorrow's capital stock for tomorrow's higher output by consuming less today. Okay, so in the case of technological investment, you are producing less today because you put more workers into R&D, but those more workers in R&D sector create better technology for tomorrow. Even if that decreases today, this will be larger tomorrow. Okay, that's the simplest way of thinking about innovation technologies. Okay. Now let me pause for a moment again, and if you have questions, I can try to clarify these things. Otherwise, I'm going to continue. Okay. So let's continue then. Now, one thing I want to show you is this. Now, let's go back to our cases of many countries, right? Suppose that particularly we are going to look at 2 countries. Okay, and let's say these 2 countries have such production functions. Okay. So this is at the output per worker level. Again, I am assuming a capital stock. Okay, doesn't change a lot anyhow. You can put it back. It doesn't make a huge difference. You can actually imagine how you can put it back as well. But remember that Y is GDP per worker. Okay. And you have YJT equal to AJT HJT, right? So typically, of course, once you look at the ratio of GDP per worker levels, you will see that productivity ratios and human capital ratios will both be important. Okay, so if you observe, this is, let's say, 6, okay, and if you observe that, I don't know, this is, let's say, 2, all right, you will observe, you will imagine that the ratio of productivities on average must be equal to 3, okay, if the model is correct, obviously. Okay, now you can also think of the growth rates, right? Because countries can also differ in research environments. Okay, so theta I could also be different. And remember the growth rate. Growth rate is theta I, gamma I star, L, A, I, T. Okay, so if you want to draw the growth rates, how do you do that? Well, you can draw it as a function of LAT. Okay, so suppose that this is growth rate as a function of LAT, and of course it is a linear function, right? So in one country, let's say I, you are here, or let's say this is J, you are here. In another country, I, you are here. Okay, so even if they employ the same level of engineers, same number, suppose that this is LAIT equals LAJT. So two countries, they both employ the same number of engineers and scientists, right? Well, what happens? Because of these differences, because of the differences in theta I, theta J, because of the differences in theta I, theta J, on one hand, okay, plus differences in, oh, sorry, I have a problem here. So this will be obviously LT. So this will be LT. This will be, oops, LIT equals LJT. Okay. So countries that have the same population will generally have different levels of growth rates. Why? Because the research environment, the research capacities, the productivity, the constant productivity of research will be different. And also the share of workforce employed in R&D will be different. Or if you draw this graph for this variable on the horizontal axis, you will see again diverging figures. Why? Because still thetas are different. Okay, so even if gammas are the same, so at that point gammas are the same, right? At that point gammas are the same, but thetas are still different. So these theta differences will create this difference, and of course here theta I in this example is greater than theta J. So even if in Turkey we employ the exact same number of engineers as in United States, possibly our growth rate in technology will be lower than the US level. Why? Because US has better universities and better research labs. Okay, so even the simplest model gives us something about understanding differences in growth rates and differences in GDP levels. Okay, so I'm going to show you later on how we can actually understand other aspects of technological progress, and we're going to come back to that point. And in fact, I'm going to show you one of my papers where I use a technological progress model, slightly more complicated than this one, to understand the contributions of different factors to Turkish economic growth in the long run. Now, let me once again pause for a moment if you have questions. Otherwise, I will continue. So you can actually do this today. So that could be a different exercise. So you can go to Penworld tables. Let me describe. So that would be a nice exercise for you. So there is this institute called Groningen Growth and Development Center. Groningen Growth and Development Center. Okay, so they have this data set on productivity. You're going to find that it is called Penworld tables. Okay, Penworld tables. So in that data set, there is one variable which is coded as RGDPO. So this is roughly corresponding to GDP at the aggregate level. Okay, then there is this thing called AMP. It is roughly corresponds to labor, LT in our models. And there is this variable called POP, which is population. So if you take, let's say, these two and define YT as YT over LT. So for many countries, you can actually get this, right? So by dividing RGDPO to AMP, you can get this data. And there is also HC, and HC is human capital. Okay, so you have HT as well. So then you can actually look at this difference for any two countries and compare and contrast it with this difference. Okay, then you will see a difference there, right? They will not be the same for any two periods, or you can actually do the long run. So you can take 10-year averages as well. So this data starts at 1950 and ends at around, I think, 2017 or 2019. So you can also look at long run averages such as 1950 to 59, 1960 to 69, 70 to 79, etc. Right? So these long run averages also could be interesting to check. Then you can tell me whether human capital differences as measured in Penworld tables actually account for the differences in GDP per worker, right? Then you can tell me, well, not always, because the reason could be technology, the reason could be capital stock per worker, or the reason could be some other things our models actually ignores. Okay, so that could be, again, a nice exercise. You can try a couple of countries, couple of different periods, and just to see how you can play with these empirical correspondence of the objects you see in the theoretical models. Okay. Now, let's make things slightly more complicated. So how much time I have? Okay, I have about 3.5 minutes. So let me pause again if you have questions. Otherwise, after the last break in the third session, I'm going to show you a slightly more complicated model, okay, of innovation again. Anything?
Hocam az önce ekran paylaşmadınız ama bilerek mi yoksa?
Ha, paylaşmadın mı? Oh, I'm so sorry.
Hayır.
Okay, okay, thank you. Unutuyorum bazen. Okay, thank you so very much. So let me share it and explain it again. Sorry. Here it is. So there is this Groningen Growth and Development Center, okay? So they have this, they have this data called Penworld tables under this section productivity, okay? And they have they have a bunch of data. Some of them are very interesting because they directly correspond to what we have in the models. One is GDP, okay? Our GDP, or is the aggregate GDP. There's another thing called labor, okay? I mean, it is called employment there, but in our models, it works like labor. So you can define by dividing our GDP O by M for each country and each year, you can actually calculate YT, right? And then you can also look at human capital because they also estimate human capital for different countries. Then you can do such calculations, right? So take any country, so to any two country and any year, and look at the ratios, okay? Ratios of GDP per worker, and compare it with human capital per worker, right? I mean, in some years perhaps they are close, but in many of the years and many countries, there will be some divergence, right? So you can understand whether technology or capital stock or some other thing that we assume away here could be actually corresponding to such differences. All right. So that would be a nice, interesting example for you to see what is out there, because theories are abstract things, and in the data there's a higher level of complexity. So trying to understand, trying to match the abstract notions in the theory with the empirical counterparts in the data could be very useful for you to understand the nature of things that we are working on. Okay, so now I have less than a minute. Let me stop sharing. So time is 2:35. So let's meet at 2:50. Okay, after about 15 minutes, let's meet at 2:50. And we're going to continue with a slightly more complicated model. Okay, so then there's something in chat. Oh, okay, all right. We already covered that. All right, let's see you at 2:50.